All right, second to last section in chapter 2, 2.9. There's two more functions that we need to learn how to deal with because they show up quite a bit, and we've saved them for the end, exponential functions and log functions. And the reason we save them for the end is because everyone likes the best for last, yeah? Yeah. Okay, so, of course, an exponential function is a function. We can use x for the independent variable. We can call it f. That what? What do you know about exponential functions? What's that? They grow exponentially. Good. They can also decay exponentially. Do they grow faster than power functions or polynomial functions in the long run, or slower? Faster. Okay. So the difference is they actually have a numeric base, b, and a variable exponent, whereas the power functions have it reversed. They have a variable base and a numeric exponent. Now the base has to take on values that work, and those values are, let's do it this way. It could be between 0 and 1, and it could be greater than 1. The domain is all real numbers, so you can't have a negative base, because if you raise a negative base to some weird power, it kind of destroys it. So we're going to look at bases being between 0 and 1, and if you recall that, that's going to be decay, like half-life, right? Half times half times half times half. When you have radioactive decay, you have half-lives. And then if it's greater than 1, it's growth, like mitosis, meiosis, the base is 2, right? They double every cycle. The graph of an exponential growth when the base is greater than 1 looks like this. They all have an initial value. One of the key characteristics of exponential growth is it has to grow out of some seeding value, some initial value. It can't be 0, right? Populations grow exponentially, but they don't grow out of 0. You have to have at least, I guess for people, you have to have at least an initial population of 2, right? Whereas polynomial functions can grow out of nothing. They can grow right out of the origin, 0. That would be exponential growth, and the domain is all real numbers. And the range, of course, is all your values strictly greater than 0. They all pass through the point of that form 0, 1. And then the decay functions, they look like that. That would be exponential decay. All right, you remember those? We've studied those quite a bit in pre-cal, and maybe even you had those in algebra 1. We are going to look at a particular base this year, right? And our favorite exponential base is not 2, but e. And, of course, e is about what? 2 point something. Yeah, it's actually 2.718-ish. It's less than pi, it's greater than 2. It's less than 3. It's between 2 and 3, but closer to 3, right? Something like that. So would that be exponential growth or decay? Growth, yeah. So let's go ahead and sketch it on our own. One of your parent functions. Horizontal asymptote. For negative values, we get e to the negative numbers like 1 over e to the positive, so it goes to 0. And it passes through the point 0, 1, and then on the right it goes up to infinity. We want to sketch the derivative by analyzing the slopes, okay? So here's what we're going to do. I'm going to choose red, and I'll choose it to be a little bit thicker. I want to analyze the slopes of this graph from left to right, and on the same axis, I want to plot the y value that is the slope. So let's look over here at this x value right here. If you were to analyze the slope right there at that point, the slope would be positive or negative. Positive, and it would be relatively big or small, relatively small. So the derivative is going to then have a y value that is exactly what you said, a small positive y value. So it might be right about there. Let's come over here to this x value, and I analyze the slope right there. At that x value, is the slope positive or negative? Positive. Well, let's just get that out of the way. Aren't the slopes positive everywhere? Okay, so the y values of the derivative, which I'm sketching f prime of x, they should all be positive. Now, it's a positive slope, but in relation to the previous one, is it bigger or smaller? Bigger. The graph is a little bit steeper there, right? So the y value now that represents that numeric value of the slope should be a slightly bigger y value than the previous one, which means it should be right about there. Over here, you get the idea. Analyzing the slope of the tangent line at that point, still a positive number, but the slope is a little bit steeper, so the y value that represents that slope is going to be a little bit taller than the previous. It might be right about there. And I can continue this argument all the way through, right? So if I look right over here, at that y value, the slope is still positive, but now steeper, so the y value that is the slope is going to be bigger. And if I kept that analysis going all the way through, it would appear that the derivative of this function that's exponential, if I connect all those dots, might first of all also be an exponential function, right? Because as I go back to the left, will my slopes ever equal 0? No, but the graph is going to flatten out, so the slopes approach 0, so the y values of the derivative would also approach 0, just like the graph itself. So it appears that the derivative of e to the x is going to be some exponential function. Would you agree? The slopes do the same thing that the y values are doing. But I wonder what the base is going to be. The way I drew it exactly perfectly on itself, right? Could it be that? Maybe. Maybe. I don't know. Could it be 2 to the x? Could it be 3 to the x? Well, we're going to let the calculator do it for us because I wasn't quantifying my slopes. I was just looking at their qualities. The calculator, remember, is a number cruncher. So let's go ahead and let the calculator, which we know it can do, sketch the derivative for us. So what I'm going to do here in y1 is I'm going to sketch e to the x. Second ln of x. There it is, in blue. And then in red, I'm going to sketch its derivative, which remember how to do that on the calculator? Math 8, the derivative with respect to x of, you can either type in e to the x again, or you can recall y1, which is what I'm going to do. And to get it to graph for all x, we evaluate it at x equals what? X. Now, zoom 6 is a good place to start, but I know what the graph of e to the x looks like. So I'm going to go from negative 10 to 4, because I know it's going to increase pretty rapidly. I know I don't need to go down to negative 10, so maybe negative 1 just so I can see the x-axis. And I'll go up to 30, and I'll turn the scale to 0. So the first one that comes in blue is e to the x, and the second one will be the derivative. You go, e to the x. Curve up, baby. Curve up. Nice. Here comes the derivative. A little slower, right, because it's crunching numbers. You go, derivative. Feel free to be your own man. You don't have to follow in the footsteps of your older brother. Ah, looks like it did. If you just look at the graph looks like it traced on top perfectly, right? So you have visual evidence that it is its own derivative, but we don't want just visual evidence. We want numeric evidence. So if you go to the table of values now, second graph, notice y1, those are the function values, y2 are the slopes values. Quantitatively, do those values at those random values of x line up? Yes. So here now is your numerical evidence that the derivative of e to the x, bless you, is what? E to the x. And you know what? It is. So let's go to this rule. The derivative with respect to x of e to the x is e to the x. So e, which really is Euler's number, Euler with an e, in this case, e can stand for easy. E to the x is its own derivative. But now without looking, what's the derivative of e to the x? E to the x. Good. It's its own derivative. But of course, the chain rule is always in the house. So if you ever have e to the blob, the derivative of e to the blob, where u is the blob, is e to the u times u prime, the derivative of the blob, right? Is there any other function that's its own derivative besides e to the x? No, the derivative ln of x is not itself. 0. Good. 0 is its own derivative. 0 is kind of boring. E to the x? A little more exciting. Very good. All right. Memorize that derivative for the quiz tomorrow. I may just throw that new derivative on there. The derivative of e to the x is? Yes. Okay.